And an interesting fact is also that it's very easy to multiply some numbers together. It's very hard to find out which special unique combination can make a certain number. So if I were to ask you guys, how would you make, for example, 143? Does anyone know? Like, what numbers would you have to multiply together? I don't think, no one really knows. But if I were to ask, can you multiply together two numbers, like 11 and 13? Does anyone know? You can use your calculator if you want. But anyways, that's obviously 143, right? So one way is super easy, and the other way is really hard. It turns out, if you scale this up, imagine you have a number that is 500 digits long, and you have two of those numbers, prime numbers. It takes a computer split second to multiply those two together, but it takes a computer, 50 years or more. You couldn't even do it 50 years to find the two numbers that make up. If you multiply together two numbers of 500 digits, you get a number with 1,000 digits, and it takes a very, very, very long time to find the two things you have to multiply together. And that can be used cryptographically. For example, the guy no one really knows who wrote the original Bitcoin paper, right? But if he put a number on there with 1,000 digits, and he later, if he wanted to ever reveal himself, he could go there and reveal the two prime numbers that made up that number. It would be a proof that it could only have been him who had made it, because he could have constructed that number by picking two random primes, multiplying them together. I hope you guys can follow it a little bit, but this is just to sort of explain where these things can come from in cryptography. And in general, they all come from these ideas that some things are fast for computers to do, and another thing is slower. The reverse is slower. So I want to talk about the one thing that you should know about cryptocurrencies, if you only had to know one thing, I guess. That's public key encryption. And this particular type, or, well, the thing I'm going to talk about now is used, in Facebook, your bank, NSA, everyone uses it. And I'm going to show you the math behind it. So you would probably expect it's super, super difficult. But actually it looks like this. It's these two things is what you need. This is called RSA for those who don't know. But basically you have to encrypt, you just have whatever secret number you want to encrypt, and you have two constants, K1 and N, and you use, you calculate this and you get your ciphertext out, C. And which is just some random other number. It could be like 3 or 18, who knows, right? And you can't really tell anything about your original message by just looking at C. That's the whole point. And you can decrypt it with two other constants, or I guess N is also used, but K2 is another constant. So you just put it in this and you get the answer out. And if you don't know what mod means, it's basically the same thing as when you have a watch on your wall, and it just, once it passes 12, it wraps around back. So right now, I don't know what time it is, maybe 7. In 24 hours, it will be 7 again, because it wraps around the watch, right? So here, that would be mod 12, because every time you pass 12, you go back. Here it's mod N, and N could be 12, but it could be so many other things. So that's basically, yeah.
I have a question. Do the values of M and N constrain each other in some way?
Yes, they do. But let's wait a little bit, please. So this is where the first kind of exercise I want to do comes in. And if you don't have a laptop, maybe you're sitting next to someone who does, or maybe you can. Well, I will go through the answers anyways after the exercises. So yeah, it's a lot of text, but it's four questions here. I want you to try whatever programming languages you like, and maybe it's Python, maybe something else. you can try and answer these 4 questions, and I will go around and like try and help people a little bit. Yeah, so I'll give you a couple minutes for that. Do you guys understand? Like, okay. Any questions? I guess. Wait. Let me just. Example code could be. Could be like. Or let's just. This would be how to encrypt, right? So the mod operator normally in programming languages, most programming languages is the percentage sign, right? You just take this to the power. I guess you would do actually probably something like that, right? That would be the first encrypt function up here.
Power of n?
It's m to the power k, and then mod n. I don't know. Oh, sorry. So. I guess I'll just go around this. Yeah, you can use calculators as well. okay, I don't know if everyone finished, but I will just go over the answers now, because not everyone has laptops. So given these numbers here, verify that it works, and yeah, it works. What happens if you decrypt the message before you encrypt it? So if you start just putting your plain message here, and then run this, and then run that afterwards, actually that works too. It's sort of it's sort of symmetric in that sense. And this is actually because K1 and K2 and N, they're intimately connected in sort of sense. So these two are actually sort of inverse in some sense of each other. And in a sense, these two equations are actually sort of the same thing. It's just another, you just take the inverse here. But anyways, so will this still work if you change either K1, K2, or N? And the answer is it won't. These three values, three constants, they're generated together. That's sort of actually the trick. This is, it's not too complicated or anything, but this is simpler. But you have, you have to change them in the same way. You have to generate them together. That's the whole trick. Then, can you calculate C? That's the ciphertext of a given number of your own choosing, given blah blah blah. This thing. And you cannot, because I only gave you here K2, which means you can only decrypt. You can't make your own message. That means that the takeaway from that is you need the K1 to create a message. You can only read messages with K2. So actually the second sort of nested question here is, my C is this thing, what is my message? And I don't know, did anyone actually get that far? 60, right? Someone say that? No? Yeah, okay, yeah, it's 60. Anyways, I can send you this message, which is 60, and you can verify that it's 60. And it could only have come from me, because I have K1. So you guys cannot never really fake messages as long, I mean, you can never fake messages from this N and K2. And that's really important. That means you can make a pair or these three constants together, and you can release either K1 or K2, and then you can send messages that are verifiably from, let's say you release K2, verifiably from that corresponding K1, and everyone can read them, but no one can fake them. So if you make K2 your public identity or whatever, no one can pretend that they're you. They can only relay your message or read your message. They can never create messages from you, right? I think it's a very good time to take questions, if anyone has. And please, there's no stupid questions. Whatever, maybe there are, but yeah.
Can you guess K1 if you have already other numbers, since K1, K2, and...
No, I cannot. You cannot. That's the whole reason why this is interesting, actually. It's a good question. But if you could guess K1, you couldn't really use this for that much. There's no good algorithm to guess K1, actually. Actually, it has to do with the thing I just told you about factoring numbers. Because n is actually two prime numbers multiplied together. That's how you can generate this two. So if you could factor n, you could do it, but you can't. So yeah, that's why it works. Anyone else? Yeah?
So to clarify, so you accidentally reveal M and C, and you reveal K2, you still can't derive K1, even though you accidentally revealed your message.
Yes.
You're still not going to release the key.
Yes, yes, exactly. You can't, yeah. And yes, that's correct. Okay. So this, I just want to say real quick, this is not the exact thing that Bitcoin uses, but it works exactly the same. The public key, which is K2 and N together, is longer for this. It's called RSA. Bitcoin uses ECDSA. That just doesn't matter. The math here is simpler, so that's why. And this is legitimately used in your bank. And when you access HTTPS anywhere, this is very likely the thing they're using. This is that simple. So yeah, so since no one can fake a message, what if M was something like send 1 Bitcoin to this other person, right? And now maybe you're thinking, how can M be, it's just a number, how can you send anything? But you can just take A and say that's 0, B is 1, C is 2, right? So you can make anything you want into a number. And now you can make these messages that are verifiably from your public ID, which is your K2, or in Bitcoin speak, it's your address, right? No one can fake this message. You're sending a message saying, I want to transfer my 1 Bitcoin to some other address. And then that other address can then later come and say, I want to do the same thing to some other address again. No one knows, no one's sharing any of the K1s. That's their wallets. That's how they keep control of, the values. Yeah, so this is how you get a transaction chain. And the chain you can verify, here I sort of just skip over how they're actually made, but let's just forget that for a second. But you can keep going back until the point where the coin was actually made, or created or whatever. So you can verify all the way back how much each address has, and if they have enough to do, to send the amount they want to send, right? So I sometimes, this is sort of a side note, but sometimes I hear like people say, oh, this makes it not real currency somehow, because it's not like a package of bytes or a physical package of something that you're giving away, And I don't really, in the end I think it's a discussion about how the definition of real should be, but the important thing is you have trust and consensus. You have to have those two, and then you can have a happy currency. If someone can create arbitrary Bitcoins, as many as they want, if it's too easy to create, then you erode trust, right? It's like in Venezuela when the government's printing money, no one wants to accept that currency anymore. They want to accept US dollars or whatever. And you have to have consensus about what one coin looks like. It's very easy in the physical real world with physical tokens. This is a bead from Congo. I think they used a long time ago. But it's very easy because one of them is just a token. Here it's the software sort of takes care of what is a token or 1 Bitcoin. So people don't have to know all these details. The important thing is everyone agrees on the exact rules. Yeah.
But is there a possibility that there's a different K1 and K2 that generate the same numbers?
It's extremely unlikely.
Like a perfect transaction?
Yeah, but you have to remember these numbers are extremely huge. You could generate Bitcoin addresses from now on to the end of the universe, and you're unlikely to hit any other. So it's not a practical problem. It's like, could you accidentally fall on your keyboard and guess someone's Facebook login? I guess you could, but it's not a good way to, it's not a good approach. There's no practical way. Practically, no, but theoretically, yeah, I guess so. But you could quantum tunnel again through Florida here, a billion, so many things could happen, right?
But there's quantum computers processing at the speed of light.
Yeah, because one of the things you could do with quantum computers is you can factor big numbers. So that's actually why they're talking about maybe they need some other public key scheme, actually. But yeah, that's a good question. But now that we know these things, there's still one problem with this scheme, even though you can verify the attention of each address and how things are sent, and that is called the double spend problem. So if you have 1 Bitcoin, or let's say bad guy A here has 1 Bitcoin, and he sends a verifiable transaction from him to both address B and C at the same time, what should happen? We need some sort of consensus. One initial reaction may be, okay, he's obviously doing something malicious that no normal user would do, even by accident. So we can just destroy his coin, just punish him like that. because it doesn't matter. Like only bad guys are punished, right? You can just not be a bad guy. But in practice, though, if let's say address A was, he sells bananas or something, and he goes to the store, buys banana, and banana guy gets this 1 Bitcoin, and then the bad guy goes home and he now sends another transaction to whatever, and then the coin's destroyed. He's still sitting at home laughing with his banana, right? And trust is then broken, so next time someone comes to buy banana, he won't accept Bitcoin anymore. So we need another mechanism. It would be sort of obvious maybe to people that the first transaction should be the valid one, so that you can't really reverse transactions, right? You can't go to the banana store, buy something, and then send to your bad guy brother afterwards, and you share the coin or whatever, or you just generate another address. So it has to be the first one that's valid, right? That's the only solution, as I can see at least. But the problem is, how do you make sure which one? It sounds so easy, but how do you make sure which order these transactions happen in, and these attempted transactions happen in? So maybe you think, well, there's a lot of people on the network, they are seeing it real time, so they would know, right? But what if someone else joined the network? Like people drop off the network and come onto the network again, and they need some way to catch up on the transactions that have happened. And how do we make sure that the bad guy can't just be a bunch of those people, virtual people that say, the wrong things? We need some kind of voting mechanism that isn't broken too easily, or it isn't broken basically. And there's a different way you could say, okay, I'm asking a bunch of people, and a person is defined by, you could say, Bitcoin addresses. But that obviously wouldn't work, because you can just make a gazillion Bitcoin addresses. And I don't even know how you would implement it, but that would just, bad guys would just make a gazillion Bitcoin addresses. And when you log on and you want to know what's the consensus on the network, you get totally flooded by these things. You could say IPs, because everyone has to pay their network internet service provider for an IP, and it's not just something you can generate infinite amounts of. But actually they're botnets, which is sort of, hackers have hacked millions of computers that they can control, and they have millions of IPs. And also, how would you even implement this? It would take a very long time to ask so many people. Maybe, well, let's not go into that. But one way that will work is voting by computing power, by proving that you spend compute power. So you have to reward people to spend compute power for this to work. I will go into it now, but if you reward people enough so that the good guys spend enough compute power on being honest, then you can have this work. And that's what's called mining in Bitcoin. So in practice, you need some way to show that you spend a lot of compute power on verifying the order of some transactions, right? So you need some kind of scheme to do that. And there's a thing in computing called hashing. And I will just very quickly explain it. It's a very simple concept, actually. This is just never used this hashing function, but basically, an example, right? If you have the number 1, 2, 3, 4, 5, 6, and this could be any number you want to hash, it could be anything. You just split it in the middle and multiply them together. The neat thing about this is very easy to go from here to here. Very difficult to go from here to here. You see? You can easily generate a hash of any number. And people use this to store passwords, for example. If you have a password, let's say this is your password, you should also never do that, but let's say it was. I could store this in my database, so even if the hacker comes and steals my database, he wouldn't be able to see my actual password. So that's what the principle about what's interesting with a hashing function. And if we wanted to generate something with, let's say, this last 3 digits were all zeros, then there's no good way other than just trial and error. We can just try different numbers, put them in, and see if it comes out zeros. And in theory, if this was a proper hashing algorithm, then this would require 500 tries on average, statistically, to guess. Right? So if I can come up with a solution, I've sort of proved in a way you can very easily verify that I've tried about 500 times to guess a correct solution. Any questions? No? Okay. So how could you do that for Bitcoins? You could create, this is called a block. You just take a bunch of transactions and you put in the address where you want your reward to go to, if you're the one who gets this hash with the zeros, right? And then you append some random nonsense here. And then you hash it, and if it's not a hash with enough zeros, you just change this random nonsense. And you just keep trying until you guess it. And in that sense, this way you prove that someone has spent a lot of compute power to vote for these particular transactions are valid, right? And you can chain them together in a blockchain, where you just take the last block hash and put it into the next one. So the block 4 would use the block hash of block 3, and you do the same things here until you have a block hash. And the trick is, if the consensus, everyone always just trusts the longest chains, then and the most compute power on the network is honest, then the problem is sort of solved, actually. So let's just go back to the bad guy and banana shop. So if this was the transaction to the banana guy, right? And now the banana guy, I mean, when he comes to the store, we are like here in time. This is forward in time, right? So we're here. The banana guy is like, okay, give me 1 Bitcoin. He does the thing on his app or whatever, and the transaction is sent to the network. The banana guy waits until he can see a block is created, verified with this transaction in. Now the bad guy has to run home, start up his computer, and try to create he wants to reverse this transaction, right? So he has to go start from block 5, try and create a competing chain. And by the time he's created block 6, maybe the other chain is already at block 7, right? And everyone just discards the shorter chains, no one cares, right? So they only believe the longer chains, and they're growing way faster than the fake chains. They're so fast that there's no reason to even try in practice, in reality.
So how long? How long do you make each chain? How do you determine how many transactions?
So there's how many transactions are in each chain? Well, it's up to the miners, I guess. The guys who verify these blocks, they just take in transactions. I guess they don't have any reason to ignore transactions, but yeah, so it's sort of up to them in a sense. And sometimes there's like, you can append fees and stuff to your transactions so that the miners get those fees if they guess it, so they have an incentive to put your transaction in there as well. But in any case, it's important to note note that the banana guy waits until he sees this is verified, right? Before he gives the guy the banana, right? That's just the time of transaction. So it normally takes about 10 minutes. There's a target time of 10 minutes. So what they actually do is, if a verification is too fast, next time they will require an extra 0 on the hashes thing here. So yeah, so that way it scales with however much compute power you have on the whole network. And so this is kind of what I already said, I guess. If you're the bad guy, you have to redo the work that was already done, and then catch up to, grow longer than the honest chain, right? And the chain, by the way, starts from day 1 of Bitcoin. It never ends. It's always just the same chain, but it could, maybe there's splits, but if they never grow a lot larger than the longest one, then people just ignore that. Yeah, and this is an actual hash I found from the end of 2016, and I counted there's 19 zeros on there. So, and this is base 16, doesn't matter. But anyways, your chance is 1 out of 10 with 23 zeros behind it to guess it. And you can, on a normal computer laptop like this one, that would take about 100 million years. So that's really, really, really long time. I read somewhere that the combined compute power of the honest compute power on the Bitcoin network is now bigger than 500 largest supercomputers. So it's really likely that it will be a good guy that guesses the next block, right? And you can even, if you don't trust it, you can wait a couple of blocks into the future. The banana guy, if he wants to, he can wait a little bit longer. Just make sure that now his transaction is buried deeper in the chain. Yeah. So yeah, that's. Anyone has any questions so far? Yes.
But practically speaking, you have to do that. You can't wait. The next transaction or the next block could be mined by a good guy, but contain the bad guy's transaction.
Yeah.
So the next one block, who knows?
You definitely have to wait for at least one block, right? Is that what you're saying?
Yeah.
Yeah, for sure.
If a bad block has like a poison record in there, there's no rolling back. You can only go forward. You have to accept it. If they're complete, just do one.
Yeah, there's no going back. The second a bad guy block would become longer, everyone would just accept that's now the longest block. That's why we're using that. So that's why if you want to make sure your transaction is valid, you would wait to finish the transaction. You would take that as a sort of transaction time, and only release whatever you're selling or whatever, until after that wait time has been completed. That's how it works in practice.
Is it the case as well that blocks can only have valid transactions, so miners would allow?
Yeah, for sure. If there's some nonsense outside the protocol or whatever, people would ignore it. I don't know exactly what they check and what they don't, but of course you can't just say, oh, he transferred 1,000 bitcoins if he didn't have any bitcoins. Even the miners can't make that stuff up. Like, they're only there to actually ensure the order of things, in a sense. Yes?
Why is a longer block better? Why is it
so it is to well.
It represents more work.
Yeah, it represents more work. Yeah, it's like it's kind of the way to vote for what is better, assuming that there are more good guys than bad guys, right? All the good guys are trying. If there are more good guys than bad guys, their chain will be longer. Therefore, we.
because they saw the block quicker, so the block time is faster?
No, because you have to. Let's assume that the good guys have more compute power than bad guys, right? So in that case, it would be really difficult to catch up for the bad guys if they want to reverse a transaction or something like that, because this one will march on at about 1 block per 10 minutes, right? And you can see also the hash rate, so the amounts of zeros that are on the hash. So that means you can easily tell how much CPU power has gone into this block, and if we believe that the good miners or the good guys have more CPU power, then this works, because in statistically speaking, the longest chain will always be the good guys' chain.
Well, what I don't understand is how more compute power turns into a longer chain.
Okay, you mean given the 10 minutes thing, or what? Or do you mean
Yeah,
just
so
general?
if you have one bad guy and he makes a block in 10 minutes, and you have a million good guys and they make a block in 10 minutes,
Yeah.
They'll make chains at the same speed.
But
No. That guy doesn't make block minutes.
yeah.
He doesn't have enough hash rate.
Okay, so hashing power is,
Yeah, compute power.
determining the speed of the chain creation.
Yes. It is adjusted how many zeros there are, but that's just a confusing technicality, I guess. In a sense, yeah, they make yes.
So who determines how many transactions go into a block? Does a block get published and then everybody competes to try to solve it?
It's just a giant peer-to-peer network. Everyone just shares whenever they see something new. So if they see like address A wants to send to address B, they just send it to everyone. And the second time they hear it, they don't send it to me. So they just propagate it everywhere. And then the miners, the good miners, just collect that. And
So but are blocks fixed size?
Yeah, for big one, they're 1 meg size. So
Yeah,
they
there's-
try and pack as many transactions into a block as they can until it gets near the limit. And
yeah.
But what's the criteria? Do we have to fill up that one there? Or kind of put 10 transactions?
I don't actually know the details about that, to be honest. But
You don't have to fill up.
yeah, I don't think you have to fill up. Yeah, this one, the one I looked at here is like only 6 kilobytes. So yeah. So, sorry.
Is the Bitcoin supply limited on some fixed number?
Yeah, so there won't ever be like, so the mining reward decreases over time.
Okay, so what happens if we mine all the Bitcoins? How would that?
We will mine all the Bitcoins, and then it will be, people have to pay these fees to attach fees to the transactions to make it work.
That would be like a blockchain.
Hmm?
Would that like more like a blockchain?
This is a blockchain. I don't. Oh, yeah.
so your question is, after the last Bitcoin is generated, then what the blockchain will continue
Yes.
with, it will just continue the transactions and would generate new Bitcoins.
So, okay, let me just go back. So, I mean, some of this, of course, is sort of simplified a little bit, but this reward here goes away. This goes to 0. But actually, what you can do when you say, when you like make a transaction like this, you can put in a fee here, some small number, and this fee, if it's in the block, then the miner will get it. He will get that fee, and it's verifiably inside here. You know? If you, yeah.
And where does this 10 minutes come from?
It's just a number that they made up. The guy who wrote the Bitcoin paper made up, actually, I think. And yeah, it's if you made it, you can't make it too fast, I guess, because then you will easily create these parts of the network that don't agree, but and it also increases the amount of. Well, you could certainly make it faster, I guess. And lots of coins, or lots of altcoins have done that.
So in order to verify that this payment to you, you see that Bitcoin is good, you have to wait 10 minutes.
Yeah, well, on average 5 minutes for one block, right? But at most 10 minutes. And actually, people often wait longer to see another block. So yeah, that's one thing. But there was for a long time the second largest coin was called Litecoin, and I believe they had a block time of 1 minute. So that was, was also an option.
Ask about the function of zeros and hashes.
Yeah.
Some hashes have more zeros than others. Does that mean that I don't understand how that would link to one of the blocks?
Yeah. Okay. So basically, when you hash something, any number, you have no idea what the hash will be, right? Only once you run the mathematical whatever, you get some number out. But you can't really start with a number and go back and say, I mean, if you wanted to get a hash that started with 3 zeros, there's no other way to do that. If it's a good hashing function, then you just try random crap, put random crap in there until you get this. That means you have to, if this is space 10, you would have average of 500 tries to get a hash with 3 leading zeros. Does that make sense?
I can't see how the zeros add complexity to the hash. It's the other
It doesn't add any complexity. It could have been like 8, or it could have been like 2 or 1 or whatever. It's just some kind of thing, some kind of special thing that you're looking for. It's like you're just trying random crap. You could say this is 1, 2, 3, 4, you know. And there's likelihood of guessing 1, 2, 3, 4. It's like rolling dice, right? You can only just keep rolling until you get this exact. It's like rolling a Yahtzee or something. You have to roll a bunch of times. If you can prove you rolled a Yahtzee, prove you rolled a bunch of times, basically, statistically speaking, it's super unlikely, right? So it's the same thing here. Everyone's just rolling for Yahtzees, and then the first person who gets it just shows to everyone else, and they get a reward. That's basically how it works, I guess.
So this mining software, is this open source? Is it very publicly verifiable?
There is some open source stuff. There's a bunch of different ways to do it, but actually if you want to be a Bitcoin miner now, they run on special purpose hardware, not CPUs like in this computer, and they have farm or like whatever server farms, whatever they call it. In China there's a bunch and other places. So it's not really, back in the day you just fire up your computer and mine, but now that's not really possible. The likelihood that you will ever hit anything is so low, so crazy low. So actually what they do also is they pool together and share the rewards. So a bunch of miners will pool together, and that way they sort of, it gets more stable income, I guess.
Is there an interest in developing better software that works faster?
There's been a ton of things. I don't know the specifics of any of this at all, but there's been a ton of things like doing it parallelized and more efficient, like algorithms for this SHA 256, if anyone cares. But there's been a bunch of things, but I'm really not that knowledgeable.
So long as the result is the same.
Yeah, anyone with a normal computer, they can download that app, and the app will, or the program, and that will verify for you easily that it is correct. Because the thing is, once you have this, with the correct random nonsense, you can hash it and you can check, oh, this corresponds to this thing that starts with 3 zeros, right? But it was getting the thing with the 3 zeros first. You had to roll a Yahtzee with this nonsense down here. That's the core idea. So it's very, very easy to verify, but it has provably taken a lot of CPU or whatever compute cycles. Yes.
Is it true that, how big is the chain now? And is it true that it can grow infinitely?
No, nothing can grow infinitely, I guess. But it's, I don't actually know, but yeah, it grows, gets bigger and bigger every year. There's a way that you can, just trust, like if you don't want the full verifiability, if that's a word, of the whole thing, there's a way that you can just trust parts of it. But I actually don't really remember how that works, to be honest.
But as a miner, do you have to store the entire
No, you don't.
You can download the chain onto your computer if you want to.
Yeah, but if you're mining it, as a miner, you have to
No.
chain at some point.
I believe you just have to have the last block hash, and then transactions and stuff, new transactions. So yeah. Yes, sorry.
There's a new cryptocurrency. What's the difference between Bitcoin and new cryptocurrency?
There's been a lot of new cryptocurrencies, and
this big one just came out. I forgot the name.
yeah, I don't know. Like there used to be. I check it like once in a while, like the list of market cap for different bitcoins, and it changes a lot, or different cryptocurrencies, and changes a lot. Other than Bitcoin being number one, it's always changing. And there used to be like kind of a wild west, because back in the day, it was legal, I guess, to take a stock on the stock market and be like, oh, this is the next big thing. And secretly, you own a bunch of this stock and it's worthless. And then once everyone buys in, you sell it. It's called pump and dump, right? And that's not legal anymore. But these tokens are not actually legal tender. It's not legal currency. So it's you could just create a new thing and just be like, oh, this is the next, whatever. And then people buy into it. And you pre-mine, you created it, so you own like a bunch of the tokens. And you just dump it, and then it's dead. And that happened like a bunch of times. But you can easily tell because it's just the Bitcoin source code is open source, so you can just copy that and change the logo to a dog's face, and then you can create a new coin. So, yeah.
With the new cryptocurrency, do you know how much the original owner has?
I think you could find that out roughly, actually. If you checked when people started using it, because there's a lot of the old blocks that are untouched, but on the other hand, people didn't care back then. I think I also had maybe 50 or 100 at some point, and I lost the address because it was worthless. It was like, but yeah, you never know, right? So, yeah.
If you lose it, you lose it. You're done.
If you lose your K1, yeah, there's no way, how can you ever retrieve that, right? So there's some interesting things you could do, and I believe some people have done it, or I believe there's some things built in to do it, but you can have, for example, you can have 3 public keys for each address, and then you can say at least 2 of them must sign a message. So if you have your K1s on different devices, you can lose one and you can still access your device or your account. I don't know more if that makes sense. Yes?
Has a bad guy ever beaten this?
Not to my knowledge, but I mean, I don't think so. Maybe in the beginning, but it's getting, it's extremely difficult now. I don't think so. Yeah, I mean, you would have to be, either that or be extremely lucky, but if you then just wait for 2 verifications, then that problem is like even smaller than that.
So what if the bad guys, for example, that small coin, they use more hashing power than the good guys hashing the same coin?
Yeah. If that were to happen, then it would all break down. But the thing is, there's so much good guys, so many good guys out there, just working for, just mining. They earn a lot of money on it. Some of them, that it's more. You would need to have more power than the 500 largest supercomputers in the world, and it would take this machine about 100 million years to just get 1 block.
For Bitcoin, but for a small coin that the hashing power.
Yeah. That's definitely the problem. But some of the mining software, if it's a direct clone with just some changed things from the Bitcoin thing, then they can in parallel try and, I don't know actually how that works, but they can, at the same time they're generating the nonsense for Bitcoin, they can do it for the other coins as well for free, basically. So a lot of them are using that as an advantage. Good question, yeah.
The Bitcoin white paper goes into why even if you could overrun the blockchain with malicious intent, it would be pointless. Yeah, just because you wouldn't run the mining rewards, because no one would trust the system.
Yeah, if you had that much.
You just destroy it.
Yeah, if you had that much compute power, then you should just be mining instead of trying to cheat the banana man, right? And if you are mining anyways, then you don't want to undermine the currency as such. You don't want it to break down. So it's a sense of sort of aligned towards not being that guy, I guess.
Has a block ever not been sold in the 10 minutes?
Yeah. This one took 3 minutes. So it's statistically based, right? So sometimes it will take longer, sometimes it will take shorter. But the target time is 10 minutes. Yeah. Yes? Yeah.
That contains some bitcoins, and that hacker used it on the market to trade it, to use those same bitcoins, I guess, public key. So is there a way that that person reports it and make sure that the miners don't, when they use the currency, they have to...
No, there's no way. And that would sort of... Yeah, that's just bad luck. There's basically, even if you could make something like that, then you would have like a third, you would have some outside authority over who gets to spend their currency and stuff, right? It's, you can't freeze coins like that in any way. But the thing they do is they encrypt your K1 on your in a file on your computer. So you have to type a password to actually get your secret key to be able to spend it. So, but I mean, if you're logging the keys as well as stealing the file, you can circumvent that. Anything else? Yeah. Well, you basically, I mean, I can send you the slideshow, and then you start from, you know, maybe you download some public key library, and then you make a thing to make addresses, and then you chain them together like this, and you know, easy, right? And yeah.
So you could just take the Bitcoin and open source software.
Yeah, but for example, let's say you wanted to have another way. You had a good idea for how to another way to solve this double spend problem, for example, or you had some other neat idea that related to this, then now you know how you could do it. But yeah, I'm not saying you should do it, but now you sort of know a little bit better how to, if you wanted to. But yeah, I think if someone were to make another solution to the double spend problem, then spending all this computing power, that would be really great. But yeah, I don't know any others. Well, that's completely decentralized.
Are you going to touch on Ethereum?
No, I'm actually kind of done now. I'm done, but yeah, unless there are any more questions. Yeah. Yeah.
Oh, what's your opinion on Segwit and Lightning?
I don't have any. Sorry. Okay. Okay. Do you have anything, Marshall?
Yeah, I will just hand it. Thanks for coming, guys. If you want to know more about cryptocurrency or any other tech topic, you can always drop us a line on Facebook or email. We have business cards at the exit. And drop us a line and suggest topics, ask questions. We can host other workshops if you want to go deeper into something. We're really happy to have your feedback on that. And we can network and talk a bit now. And I guess those guys want to close the office quite soon. So we can go to the refinery on Habatun. I think it's 72 Habatun. There's a bar there, it's quite quiet, so we can keep talking and network, grab a beer and discuss more. So thanks for coming, guys.